Assalamu alaikum. My name is Professor Muhammad Khair Kassir. This is the first lecture in the electrodynamic course 731. The first thing I will explain how to generate the Legendre polynomial by solving Laplace equation. We know that the Laplace equation for the potential phi is given by del square phi equals 0 and has the solution 1 over r. Also, we know that del square d phi by dz equal 0 and d phi by dz must be a solution for this equation. So phi 0 is 1 over r now. R is the square root of x squared plus y squared plus z squared, which is 1 over r times 1. 1 is b0 of cosine theta. Phi 1 is d phi 1 by dz, which is z over r squared, which is r cosine theta over r cubed, which is p1 over r squared. Now d phi 2 is d phi 1 by dz, which is 1 over r squared minus 3z squared over r to the power 5, which is 1 over r cubed, 1 minus 3 cosine squared theta. This is the p2, and so on. Now we have to expand 1 over x minus x prime. We know x represent a field point and x prime represent a source point. This is the potential due to a point charge of 1 electrostatic unit. This is given by summation over L from 0 to infinity r to the power L over r to the power L plus 1 PL of cosine theta. R smaller or greater means that if r prime is smaller, you put it in the numerator. If r is the smaller, you put it in the numerator. The detail of this is given by this expression. Now, if the potential we have, or the distribution, possesses azimuthal symmetry, we can expand this along the z-axis. We know that 1 over x minus x prime is given by this expression in terms of Legendre polynomial. Now along the z-axis theta is equal 0, so PL of cosine theta is equal to PL of cosine 1, which is equal to 1. Substitute in the above equation, we get this final expression. Now the detail of the previous work is given in this slide. Now I am taking r prime along the z-axis, and the case when r is greater than r prime, phi is given by this expression. If r is lesser than r prime is given by this expression, and if I is greater than r prime, it is given by this expression. Now from this we can determine a sub L and b sub L by expanding 1 over r minus r prime. Depends which one is bigger. So if you proceed, you can show that a sub L is given by 1 over r prime L plus 1. In this case, r prime in the denominator. It means that it's greater than r. For r greater than r prime, we have 1 over L summation over L equals 0 from L equals 0 to infinity, r over r prime to the power L. So we can get b sub L. This is the final expression for this expansion. Now let's apply this to a problem which possesses azimuthal symmetry. This problem is a circle or insulating ring which has a charge Q distributed uniformly on the in the ring. The radius of the ring is A. I have to find the potential at the symmetric axis at Z on the Z axis in two cases, when Z is greater than the radius of the circle and when Z is lesser than the radius of the circle. We know that the potential at a point Z is given by Q over the square root of Z square plus A square. Now we have to find a general solution for phi if the point is located somewhere in the space. Now, in this case, I want to remind you that m is equal 0, that's no phi dependence. The phi coordinate is called an ignorable coordinate in this case. Now, we have to solve Laplace equation in a space. We know that the solution is given by phi of r and theta equal summation from L equals 0 to infinity A sub L r to the power L plus PL over r to the power L plus 1 PL of cosine theta. Now, as I mentioned in the previous slide, to get AL and BL, we have to expand phi of Z. Now, we first take the case where Z is lesser than A. The second term on phi, which has the powers 1 over L to plus 1, is divergent at 0. Therefore, all BLs must be equal to 0. If we expand for a point where Z is greater than A, in this case, the first term diverges at infinity r to the power L. Therefore, we take all ALs equal to 0. Now let's proceed by expanding this quantity Q over square root Z plus A square. Now you push for A greater than Z. You push A outside the root and you expand 1 over plus Z over A squared to the power minus half as a polynomial expansion. This is the expansion. A simplification of this gives you this final expressions. Note that 2 to the power k times k factorial is 2k double factorial. Now after that, the solution is a sub lz to the power l. And if you compare this with the expansion, you can find a sub l. Actually, l is an even number. As you can see here at the bottom of this slide, l is an even number. And the final step, you have to replace Z by R. Another example is that the cylinder now the same circle, but the center of the circle at point B on the z-axis. Now phi in this case equal q over square root of r square plus c square minus 2cr cosine alpha, where c square equal a square plus b square, means that alpha is tan inverse a over b. This is the generating function of the Legendre polynomial. We can, for r greater than c, write phi equal, we take the point along the z-axis, the field point, equal q times L from 0, summation from L equals 0 to infinity to the power L over L plus 1 PL of cosine theta. What, as we did in the previous example, once we are done with these constants, we have just to multiply by PL of cosine theta. So the solution is given by Q equal by phi equal q from L equals 0 to infinity r smaller to the power L, r greater to the power L plus 1 PL of cosine alpha PL of cosine theta. The final solution now in terms of z is given by this, by the expression for the second expression in this slide for z for z smaller than c, and the last expression is for z greater than c. Now we have to replace z by r. So the solution is given by q times the summation from L equals 0 to infinity r lesser to the power L r greater to the power L plus 1 PL of cosine alpha BL of cosine theta. Now in the next lecture we will find the full solution for the Laplace equations at where m is not equal to 0, no azimuthal symmetry exists, and I hope we have time to discuss with you homework number 1 in next lecture. See you.